Hi, Margaret. This one's going to be probably kind of long, but I'll just try to be really efficient, and then you could pause it, at any point. So this is my PowerPoint presentation on energy in chemistry. Now, people study energy a lot when they take physics classes, and maybe you'll do that, but we're just going to look at the equations that energy is involved when you're taking a chem course. So things like, how do you calculate an energy change with some kind of chemical process? What's the difference, or what's the connection between energy in the form of heat and in the form of work? Those are two different forms of energy transfer. So I want to do this explicitly. Heat uses the letter Q, and work uses the letter W, and both of them are energy transfers. It's not really right to say, oh, hot water has a lot of heat in it. It would be appropriate to say, hot water has a lot of energy in it. Now, if the hot water or the hot beaker here gives energy to something else, so let's say the air, well, you would say the Q, that's the amount of energy that got transferred. That's why I made a difference between something that's being transferred and something that's being contained. Later this semester, or even next semester, you're going to talk about equilibrium, so you don't care about that right now. So I mentioned these two terms. Work is W. Notice that it's lowercase, and heat is Q. That's work. Chemistry people usually care about work in the form of the production of gases or the production of electrons. What do I mean by the production of gases? Let's say you did a chemical reaction and it made bubbles of, let's say, H2 gas. You would say that the chemical system did work because those bubbles have to push against the atmosphere. On the other hand, if you do a reaction, let's say, that forms a reaction in which the temperature rises, you would say that the system gave off heat energy. And so sometimes, let's say, you could add an acid like HCl to a base solution, and that's a neutralization. You're not producing any bubbles, but you are producing heat. Now, I mentioned that physics cares about energy also, but they use equations like this, like kinetic energy, 1/2 mv squared. You don't really do that equation much in chemistry, but these are the kinds of energy that you would consider kinetic energy, like things that are moving, motion of particles, a car moving. Electrical energy, where you have electrons going through a wire, that's kinetic energy. Sound, all of these things are kinetic energy. Potential energy is a form of energy where it's associated with the position of something or the composition. And so the position of something might be, if you have a book on the edge of a table, this book has the potential to cause the mousetrap to flip. So that's potential energy. That's the form of energy that's based on position. Composition, that might be something like this molecule, octane. Because you have this molecule is made up of C and H bound in certain ways, it has the potential to form CO2 and water. I realize this is not balanced, but also a lot of heat energy. That's why we use octane in our cars, because it has the potential to generate a lot of energy. Here's a version of a chemical reaction that involves a change in potential energy. So let's say, for example, you had some electricity hooked up to, you have two electrodes here, and you could actually take the water and split it into hydrogen and oxygen. This is a case where the hydrogen gas contains stored potential energy because it can be burned at a later time. So in effect, you could think of the energy was inside the battery, but now the energy gets converted into the chemicals. So it's kind of like you're going uphill where the H2 and the O2, all of these molecules are higher up than the molecule you started with. And how were you able to climb that hill? Well, with the electricity. So you took electricity and you caused the molecules to create more potential energy, as opposed to the gasoline engine, which does the reverse. A gasoline engine like C8H18 takes the potential energy and it converts it to something more stable. And so you know, of course, that that's an exothermic reaction. The energy gets put out into the surroundings. Now, I've used a couple of words here that I'm sure your professor used: the system and the surroundings. So the system in this case, you could just say, oh, it's the orange stuff in the liquid and inside the flask. That's the system. And everything else in this picture is the surroundings. There is a subtler way of defining a system. For example, you could call the system just the molecules that are reacting. Let's say if you mix an acid and a base to make water in a neutralization, you could say that this is the system. And so if you had a flask, for example, where the H plus and the OH minus is the system, and then if you have a thermometer inside the solvent, you could actually consider the solvent the surroundings. This is going to become really important in calorimetry because the sign, let's say there's a Q of the system, that's going to be the negative of the Q of the surroundings. And many students make mistakes in screwing up the sign of these things, but I'll talk about that more later on. So it says a meaningful study of any transfer of energy requires that we clearly define the system and the surroundings. Those things together are the universe, and you could talk about the internal energy of a system. It's the sum of all the potential and kinetic energies of the particles present. The total energy of the universe remains constant. A change in energy of the system, therefore, must be accompanied by an equal and opposite change in the energy of the surroundings. So if you look up here, let's say there's some change in the system, well then the surroundings has to have the negative change because the universe doesn't change. Okay. It says energy transfer as heat, that was Q, remember, will occur spontaneously from an object at a higher temperature to an object at a lower temperature. So if you have a hot piece of metal, and you may have done problems like this already, and the water is cold, what we're saying is that the energy lost by the metal, by the hot metal, that's going to equal the energy gained by the water. So we're going to learn some equations for doing that in a second. The transfer of energy as heat continues until both objects are at the same temperature, and then you say what you have is thermal equilibrium. At thermal equilibrium, the object with the temperature increase has gained thermal energy, and the object with the temperature decrease has lost thermal energy. So the thing that gained thermal energy here, the water, the Q of the water, this is going to be a positive number because it gained energy. The Q of the metal is going to be a negative number, which is why you have to put a negative sign in front of the Q of the metal in order to make this an equal. Energy diagrams for the transfer of internal energy between a system and her surroundings. Oh, so I don't know, when this program didn't transfer this correctly. These are deltas. My textbook uses delta U, and a lot of textbooks use delta E. So I just put these both in here so that students wouldn't be confused if they saw either one. So if I mentioned earlier that if you have some initial state that's high and a final state that's low, then you would say that energy is released to the surroundings. So in that case, the delta U of this system is going to be negative. Over here, the delta U of the system is positive because it absorbed energy. So you might say the initial state, let's say this is a raw egg, and then you would say the final state is a cooked egg. The egg has gained internal energy by being heated from the surroundings. So you could consider the stove as the surroundings. Here's two cases where energy is transferred just as heat. So this is hot water, and this is cold water. And you would say the Q is going to be negative because it lost energy. We'll learn an equation mc delta T. The m is the mass of the water. The C is the specific heat capacity of the water, and delta T is the change in temperature. It's the T final minus T initial. For the ice water and the room temp water, the Q of this system is going to be positive. mc delta T. The final temperature is higher than the initial, so that's positive. This is, of course, mass is a positive, and the specific heat is positive. All right, over here, yeah, it was negative. Here's a case where energy transfers in the form of work. You don't see this a lot in chemistry, but I think it's worth showing an example. So here, if you take, this is the before, this is the before, this is the after. The before takes zinc metal and it puts it in a hydrochloric acid solution. Notice what happens. You make a bunch of bubbles. The bubbles are H2 gas, and the bubbles create this purple gas, and it pushes on the piston. So this is a case where the system does work. It loses energy. So in this case, the work would be a negative number. The delta internal energy, which was in the form of work, is negative. So the system before was at a higher state, and after was at a lower state. So this yellow downward arrow is an indication that this is a negative number. What if we did the reverse? What if you started with a bunch of gas in contact with the liquid and then added a bunch of pressure? So now the final pressure of the gas is high pressure gas. Well, the picture kind of tells you what's going on. You start at lower energy, you end up at a higher energy, so therefore the work that's done, the work on the system, is a positive value. The system gained energy. By the way, again, I know the slides say capital E, but my current textbook changed it to delta U. I don't know what your textbook does. So this is a slide that explains something that's important about why we use certain letters, lowercase and capital. State functions use capital letters. State functions are path independent. So something like delta U or delta E, those are capital letters, they're state functions. Q and W are path dependent. And here's what I mean. Take a mole of gasoline, let's say, and then you combust it. It makes a difference how you burn it. Now in this picture, on the left, they've taken gasoline and put it in a garbage can and just thrown in a match. It's the same chemical reaction that you would expect. You are burning octane to give CO2 and water. That always happens when you burn a hydrocarbon. Notice that the way this arrow is drawn, the vast majority of the energy that's released is in the form of heat. Now this arrow is actually a little bit of a lie. There's a tiny amount of work that's done. Because as you produce CO2 and water, you are pressing against the atmosphere. But in terms of a percentage, it's just a tiny amount. Most of the energy is released as heat. Take a look at burning octane in a car. Now, when you design a car, you use a piston, and you burn a little bit of gasoline in the piston, and the expansion of the gases pushes the piston up. So a vast amount of energy is used as work. Now, of course, an engine gets hot, so some of this that goes in the form of heat, and so there's a sum there, and look how the artist drew this. They drew some work and some heat. The value of these yellow arrows going down is exactly the same. So delta U or delta E, that's the change in the internal energy, again, it doesn't matter what letter you use, is exactly the same. But if you go by the right-hand path, the Q and the W are about the same. They're both numbers that are kind of competing with each other, where if you just burn the gasoline in the garbage can, Q is way bigger, way bigger than the amount of energy in the form of work. So what this slide hopefully illustrated for you is that the change in the internal energy is the same, the length of the yellow arrows, because it's a state function. The value of Q and W are different because they're not state functions, they're path dependent. When I say that a system does work, it's kind of gets called this name called pressure volume work. So let's say that you had a compressed gas here, and this disc was held in place by some metal pins. As soon as you release those metal pins, the compressed gas is going to push against the atmosphere, and so this system does work. The equation that you use to solve for how much work is done is the work that's done is minus P delta V. So P is whatever the pressure you're pressing against. Probably here it's like atmospheric pressure. Might be 1 atmosphere, might be some similar number. And the delta V is the change in the volume. You're comparing the before and the after. Notice that the change in the volume here is positive, but you know that the system does work. The system lost energy. How do you know that? Because this gas used to be compressed, but now it's just normal pressure. So this system did work, so the system lost energy. So that's why that this formula has to have a negative in it, because you know ahead of time that this is going to be a negative number if this is the picture that it does. All right? This slide shows you that you have to analyze each system independently to see how they add up. So if both Q is a positive, that's a gain in energy, and the work was a gain in energy, you know that the delta U has to be positive. If the system loses heat energy and does work, which is a negative value, then you know that delta U has to be negative. These two situations, you need real numbers. You need to know the sizes of Q and W to figure out what the sign of delta U is. So let's do this problem and see if it makes sense based on what you just learned. When gasoline burns in a car engine, the heat released causes the products CO2 and H2O to expand. So gas plus O2 goes to CO2 plus H2O gas. And it expands. Okay, it does work. It says it pushes the pistons outward. Excess heat is removed by the car's radiator. I'm going to use a different color just to show you that. So I'll use yellow to represent the heat. Heat is expelled. Okay? If the expanding gases do 451 joules of work, and the system releases 325 joules as heat, calculate the change in the internal energy in joules, kilojoules, and kilocalories. Well, this is an example of something that we call the first law of thermodynamics. The change in the internal energy is going to be equal to the heat plus the work. And so for us, we had a value of heat of negative 325. Why did I say that? Because the heat is expelled. The system's losing energy. And the work that's done is also a negative, because the system, you have to read it carefully, the system does work on the pistons, so the system lost energy. So therefore, the change in the internal energy is going to be this sum. So it's negative 776 joules. I'll let you do the conversions to kilojoules and kilocalories. And look what we did. Okay? Margaret, I'm going to take a break on this because I need a drink of water. I'll send this to you and I'll pick it up on slide number, looks like 17 on the next thing. Bye.